here. Hello, everybody. So it's 8 p.m. GMT, and it's time for our webinar on vector symbolic architectures and hyperdimensional computing. Welcome, everybody. And before I will hand the word over to Antonello, who is the speaker today, I want to quickly draw your attention to our beautiful website. And there is a new information available. So our winter session for the next year starts to get shape. So if you go here and have a look, so we have already talks, confirmed talks until almost, let me see, the end of March, which is good. And as you can see, the talks are extremely exciting, touching on different aspects of VSA HGC. So, and saying that, I also want to draw your attention to some vacant slots. So if you have an idea whom you want to hear, or maybe you have your own information to share, so please feel free to contact me at any time. So, and the slot will be yours. So I will stop sharing my screen. And now with a pleasure, I want to introduce Antonello Rosato. And so without any further delay, so the floor is yours.
Thank you, Evgeny. Hello, everybody. Let me share the screen so I can tell you all about hyperdimensional computing in distributed randomized neural networks. I'm from the University of Rome La Sapienza, and this work was done in joint conduct with Massimo Panella, Denis Clero, and Evgeny Osipov. So we are talking right now about distributed learning. Some of you may actually know this, and some of you may not, but there are several contexts with which intelligence is scattered around the space. And there are several agents that are working in a cooperative way to solve some problems, which can be classification problems, prediction problems, or general inference in the information domain. For some example are edge computing, sensor networks, low power computing, and so forth and so on. In these cases, when those single agents are distributed, often the capacity is thought to be reduced because they are scattered around the network, the communication, and the communication can be costly between among these agents. Furthermore, data is very difficult to share or move in contexts where we have low complexity and low capabilities agents and sensors. There's also another issue, which is privacy. There are some cases in which, if we think about biomedical application, for example, privacy is indeed an issue, and so data is impossible to move. And for these reasons, we will work in this distributed learning framework with randomized networks, which are networks that are less computationally extensive in terms of training and inference. The randomized neural networks, as always, some of you may know it, they are just neural systems where the majority of the connections are fixed. They are fixed either stochastically, in a stochastic fashion or deterministic fashion, and the training algorithm is limited to just a subset of the weights of the network. Sometimes these randomized neural networks are used to analyze the properties of neural networks and to gain insights on the inner mechanisms of neural networks themselves. They also are getting a resurgence in recent years because they are being extended to deep models. And for the reason that I said, so since the training algorithm is limited, they are the ideal test bench for distributed techniques. We will work with randomized vector functional link networks. It's just one of the many examples of the randomized network domain. They are feed-forward neural network, and they are composed by, in our case, by three main layers: the input layer, the hidden layer, and the output layer. The connections between the input layer and the hidden layer are fixed, and are assigned randomly. And the connection from the hidden layer to the output layer are instead trainable. We will use it in a classification problem, and so for this reason, for this particular problems, we have a classifier that is WOUT. It's called WOUT in our case, and it can be obtained by regularized least squares. How we gonna do with what we gonna do with hyperdimensional computing and vector symbolic architecture to exploit the structural RVFL? First of all, we will use the binding and superposition operation. Then we will use the clipping function to limit the range of values of the hypervectors in the superposition that I will explain in just a second. So in our case, the RVFL with HDC will have just one hidden layer. The values of the features will be projected in a hyperdimensional space using the thermometer code. And the random projection will be from input to the hidden layer, so the fixed connections. So the weight matrix of this fixed connection will be random and bipolar. And the output matrix instead will be trained. This is just the example of a thermometer code n equal to 4. So the network begins by quantizing. This is the network structure, and we will add here our density-based representation layer, which will make use of hyperdimensional computing theory and applications. The network begins by quantizing the values of individual input features from the input samples, and each feature is then represented, as I said, in the form of these bipolar hypervectors that are collected and stored in this density-based representation layer. Then we use these thermometer codes and we bound them with random bipolar hypervectors that are assigned to each feature at the initialization step of the RVFL network. And the resulting hypervector are stored in the matrix Win. Then we have the results of the binding of a single feature is simply the binding between the matrix Win and the hypervector features of that particular feature. And this gets sent to the hidden layer, and then it's used. The clipping function is used as a nonlinear activation function in place of the TANH, which is often used in this kind of network. As I said, we will use these for classification problems. So we will define two different classifiers, and by the winner takes all with the largest activation function at the end of the output layer. And the two different classifiers, one will be the regularized least square standard version of the classifier, and then the other one will be what we call the Centroid Classifier. The RLS classifier is the standard solution, as I said, and it just minimizes the mean square error between the ground truth, which are just the labels of the classification, and the output of the network. As a one-hot encoding. The activation of the hidden layer for all the samples are in this activation matrix, and the classifier is obtained in a single analytic step. That involves matrix inversion, and we also can call it like a technique of regularization, which involves, as I said, the transposition and the inversion of the matrix. So it's a computation can be a computationally extensive way of dealing with this classification. On the other hand, we will make use of the superposition operation from the HDC world, and the classifier WOUT will consist of individual centroid for each of the classes that need to be classified. The main idea for this is that these centroids that are representative for the individual classes might provide high between class variability and low within class variability. So in other words, they can be thought as a good representative of each single class they are representative of. Because in the layer activations are the idea is that they're going to be very similar to the class centroid. In this case, we have just a much simpler computation that is reported right here. And this will enable the actual distribution because, as I said earlier, when we deal with the distributed framework, we need to exploit the possibility of having smaller capacity in computational capacity in each agent. As the title says, we focus attention on distributed case where a set of agents is scattered in the network. So they have their own computation and communication capabilities. They have their own local subset taken from a full data set that is spread over the network. In our application, we consider these subsets being sampled independently without replacement from the full data set. And each agent can communicate with other agents in this interconnected network. We model the network as a directed graph, so with an adjacency matrix. And to wrap it up, there are three main constraints in this distributed framework, which are general and can be applied to any distributed framework that we can think of. And there are that no agent is allowed to coordinate the training process. So there is no actual centralized authority. Agents are not allowed to share data samples. This is for the privacy constraint that we said in the beginning. So they are only able to share other information about their classifier, either the weights or other higher representative of the data. And the communication is allowed only between connected agents at step one. So if two agents are actually connected one to the other, they can communicate. If they are connected through another agent, in this case, we're thinking that they do not communicate, are able to communicate and contribute to the distributed solution. This is the procedure in brief. Each agent obtains its local classifier using its local training sample, then gathers the classifiers from its own neighbors, and then each agent combines the classifier in an aggregated one. So we will not use an iterative approach. We will not study the convergence because we are thinking it as similar to a one-shot average of the single local agents. It is very important to know that since we are so we use randomized neural networks to be able to deal with decreased computational capacity, but also we need to deal with decreased connection capacity and data transfer capacity. And for this reason, we would like to compress the information to share in the network to reduce the communication costs. And for this reason, we use the holographic reduced representation model, and we use the binding operation of this HDC and VSA to realizing it via the circular convolution, which is visualized here in these slides. And it's just the outer product of the hypervectors that are being bound. So we have random hypervectors that are corresponding to key-value pairs, where in each pair a value is a classifier for a single class, and the key is a random hypervector corresponding to the same class. And we bind them and via the HRR circular convolution, and we get a compressed version of the classifier at each agent. This is much less large than the actual classifier for the RVFL, for the single RVFL, and that's the advantage that we can actually have a decompression step after the agents communicate their own classifier to reconstruct the approximate version of the W out that was sent. To be able to evaluate this overall framework of the distributed RVFL using hyperdimensional computing, we choose three different classification models. The first one is the centralized version. which is, of course, not feasible in our case, and is just used as an upper bound benchmark. So we are basically saying, what if the data is gathered all in a single agent? So information is all available for a single agent. And this is, of course, the most, the one that will have the most the highest classification accuracy, because, as I said, there is all information gathered in one place. Then we have the local version. In the local version, each agent is in the network, but is not able to communicate through this network, and has access only to a local subset of data and its own training data, and thus is expected to be the lowest accuracy one, because while trained appropriately, it has only access to just a small amount of information referring to the overall classification problem. Then we have our distributed version, which is the one that I just explained in detail. And in this case, we actually share each agent can share in this network the locally computed classifiers, and either as they are, or or with a compression procedure with exploiting hyperdimensional computing. As I said, in this evaluation setup, we will see two ways of forming the classifier: the regularized least square and the centroids, and we'll compare the classification accuracy of both ways with these local, centralized, local, and distributed version. What we expect is that centroids have a trade-off between accuracy and complexity. So, but they are actually enabling the distribution of the solution in a smart way. We did these tests on the UCI datasets, UCI machine learning repository that are very well known, but we used only the highest numerical datasets that had more than 1,000 samples in the training part. This is because we will see that we carried out experiments for a different number of nodes in the network, different number of agents in the network, and to be able to don't make the networks of the single agent underfit due to a reduced model, to the reduced data. This is the first experiment. We got the centralized setup, and we just wanted to see how the regularized least square compares against the centroid. We averaged it over 10 runs, and we cross-validated. These are the cross-validated accuracy obtained by each of the classifiers. So each point is one classifier. The Pearson correlation coefficient between the result was 0.8. And this indicates that there is an high dependency between the results. However, we can clearly see that the RLS actually outperforms the prediction obtained from the centroids. And in this regard, the average accuracy for the RLS was 0.8, and the mean computed on all the datasets for the centroids was 0.7. At the same time, it is worth noting that there were numerous datasets in which the actual performance, the actual accuracy were very close, and less, actually numerically less than 0.02. So this means that, in other words, for approximately a quarter of the datasets, the centroids classifier was indeed a viable option. And while the centroids are very simplistic, the classifier can be still seen as a useful approach. Then we jump to this more complicated visualization of the experiments. So we have the local and the distributed versions plotted against the centralized version. Each row is one of the two different classifiers. The top row is the centroids classifier. The bottom row is the regularized least square classifiers. And each column is for a different number of nodes in the communication network. The first one is for 10 nodes, the second one is for 50 nodes, and the third one is for 100 nodes. These results have been taken without considering the compression with the HRR convolution. For every experiment, we used local independent subset for both training and test. And then we computed the average accuracy of the whole network of agents. And from these graphs, we can gather several interesting observations. First of all, the distributed version clearly outperforms the local one. So this brings the performance very close to the centralized version. And this is very desirable. And it means that our actual distribution information is doing something to the accuracy. So it is working in some sense. And it justifies that the exchange of information among the agents has a positive impact for the classification performance. Other observations are that for both classifiers, so the centroid and the RLS, the local versions are getting worse with increased number of nodes. This is also unexpected. Well, it is not unexpected because since we sampled between the agents without replacement, the amount of training sample provided in a single agent was actually decreasing with increasing n. And something that maybe I did not mention is that we consider the fully connected case. So each agent is connected with step one with all the other agents in the network. When it comes to the distributed classification, the results for the centroid classifiers always matched the centralized version. And these results is also expected because in our setup, after exchanging the local centroids, each agent should obtain the exact replica, or at least similar, the exact replica, because there is no compression of the centralized version of the classifier. The situation is a little bit more subtle with the RLS classifier because it's clear that for any number of agents, the distributed version is better than the local one. And this can also be seen from this summary, this table of the results without compression, in which we can also see, these are the accuracy, of course, the mean accuracy. We can also see that the relative improvement of the distributed version over the corresponding local version is increasing with n. So this is a further proof that our distributed approach works better when there are more agents in the network, even if the actual datasets of the local datasets are shrinking in dimension. Overall, we see that the results were decreasing with increasing n, and that is with increasing number of nodes in the networks, and that is because aggregating together local RLS classifier is not equal to computing a single classifier from the full dataset. And so we do not see the same performance as in the case of the centroid classifier. Here we reported the results for the local and distributed versus the centralized version with compression. So the circle, the blue circle and the blue and red circle and square markers correspond to the results from the previous experiment, and for the local and distributed version. Then the asterisk markers in black are corresponding to the results of the distributed version with compression. So we are evaluating how much we are losing in terms of accuracy by compressing the actual classifiers. And the centroids classifier provided some unexpected results, since for some datasets, the accuracy was higher than that of the centralized version. We think that the cause of this effect should be in the fact that for some of the datasets, the noise introduced by the compression procedure was acting as some kind of regularization on the classification. But nevertheless, there were also datasets for which the distributed version with compression performed worse than the local one. However, the accuracy for 10 agents in the network was the same for the local as for the local version and the distributed version by mean values. For larger values of agents in the network, the average accuracy was higher than for 10 nodes. So this is actually one further proof of our distributed approach. One important one important remark that we can take from this result is that the average accuracy of the distributed version with compression for 50 nodes and 100 nodes or agents in the network was the same as for the distributed without compression and the centralized version. So this means that we are actually not losing important information by compressing the classifiers. And so we are enabling it to be deployed on network structure with low communication capabilities. The results improved for larger values of n, as I said, and the difference with and without compression was shrinking with the number of nodes. So after we proved the effectiveness of our compression approach and our distributed framework for RVFL networks, we moved to evaluating how well we were compressing the W out of the single classifier before sharing it with the other agents. So we did some tests with 5 different scenarios. First one, it's the uncompressed version. So this is the baseline. We use the optimal size of the hidden layer. We do not compress the W out, and we transfer it from agent to agent as is. So this will be, of course, the optimal one. Then we have a lossless compression that is used using the zlib deflator algorithm, and it's a public domain algorithm, and combines this algorithm with DAF1 coding. And this is a baseline for how strong is the gain of our proposed approach of compression in terms of information, of how well we are compressing the information. Of course, this lossless compression is completely impractical in the sense of deploying it on distributed architectures, and we are just doing it to be able to know how well we are compressing the data. Of course, when we use the lossless compression, we will see that the classification performance of the model is the same as the uncompressed version. And also the compression ratio, so how hard we are compressing the data, is not changing. We cannot dial it in because it's just as is. Then we have the lossy compression, which we implemented operating some dimensionality reduction using a truncated SVD, singular values decomposition, and in this case we truncated the eigenvectors to be able to actually have a reconstructed matrix W out, which will bear some difference with the original one, and in this case we were actually able to by truncating it more or less be able to regulate this compression ratio. Then we have our lossy compression, which is the one that I just explained using HD computing. And then we thought about comparing those 4 scenarios with a small model. By small model, we just mean that what if we used an uncompressed W out, but we just decrease the size of the hidden layer to match the compressed version of the W out for the optimal size of the hidden layer. And in this case, we will see that because this is, of course, this is an option to compress the information in some sense, because we are not using the optimal larger hidden layer size. So these are the average accuracy for 10 agents. And we performed the experiments in the distributed scenario with both procedures for both classifiers. So on the right, you have the centroids in red, and on the left, you have the regularized least square in blue. The accuracy is on the y-axis and is plotted against the compression ratio. The vertical lines, of course, as I said, stand for the lossless compression accuracy, which is fixed. And the horizontal line is the uncompressed baseline, which you will see at the top part of the figures. Let's get to the analysis of these graphs. For both classifiers, the baseline acted as an upper bound, and this, of course, is expected. And there are some losses introduced to the classifier during the decompression incurred, and this decreased the classification performance. Of course, also, the accuracy of both classifiers were getting worse with the increased compression ratio. But given the same ratio, the RLS classifier always outperformed the centroid one. And in the case of the centroid classifier, small models, so it's the dashed dot line, were very close to the uncompressed baseline. And the explanation for this is that to have a fair comparison in the experiments, we use the size of the hidden layer optimized for the RLS classifier. So maybe the centroid classifier is much simpler and it will need smaller sides of the hidden layer to get most of its classification performance. So it is a small model in the centroid classifier, but we didn't tune how small was it. And in contrast, we can see for the RLS classifier that for a small compression ratio, so around 2 or 3, the compressed classifier and the small model were performing on a par. But when the compression ratio was increasing, the compressed classifier was performing better than the corresponding small model. And these are the results for average accuracy for a network of 100 agents. And also we can see here that we have a similar behavior, and with respect to the SVD-based compression, for the trend of the results in terms of accuracy and compression ratio trade-off was indeed expected. And in particular, the mean values follow the same trend as for our proposed compression approach, with the difference that the achieved accuracy was always lower. This, we conjecture that this can be likely caused by the fact that even least significant eigenvectors bear important information about the classifier. So when we truncate it, the decompressed classifier misses actual important information. But it is indeed further proof that our compression approach is kind of balancing out all the edges of these other compression approaches. Let me just say one other thing, that in this case, distributed as SVD and HDC were noticeably better than the small models. And this is expected because in the proposed approach, the noise introduced to the compressed classifier gets kind of averaged out, and the more classifier gets aggregated, the better it is for mitigating the noise. So this is also something that we need to bear in mind when we are deploying it with small number of nodes in the network. In the previous experiments, we just compressed the classifier, but we know that, and there were some talks also on this, that if we can quantize the classifier, the neural networks are usually very able to solve the same problems using the same task. And it is so, quantization it needs to be considered to reduce the dimensionality of the classifier instead of compression. So we carried out some tests just for the centralized case to explore if it is worth considering the quantization before compression. And in this figure, we present the average accuracy of the RLS, which is the dashed dot line, and the centroids, which is the dotted line, and the classifier, which are uncompressed on the data sets against the number of quantization levels. So the accuracy is on the y-axis and the number of quantization level is on the x-axis. What we can see from here is that when the W out of the classifier of the RLS was quantized to very few levels, so around 3 and 5, the accuracy was affected significantly. But it is also clear that for the increased number of quantization levels, the accuracy for both classifiers started to reach their unquantized baseline. This is true both for the RLS and for the centroids. Also note that in the proposed approach, with the compression version of the W out can also be represented with fewer than 32 bits per weight. And it is expected that decreasing the precision will just add some additional noise during the reconstruction. Obtaining the quantitative results to characterize the effect of this noise will be a part of the future extension of this work. Speaking of future works, we definitely are working on sampling with replacement against this siloed data model that we used here. So where different agents can have similar, the local subset can overlap with respect to the overall data sets. And definitely the other strategies for splitting data among agents also in more efficient way or less efficient way will be carried out. Some tests will be carried out on this. Another thing is unbalanced capacities, because now we are supposing that each agent has, it is the same model in each agent. So in reality, it can happen that different heterogeneous capacities, heterogeneous sensor, heterogeneous agents can work together in a cooperative way, and they will have imbalanced capacity. How does this actually affects the computation and the classification problem? The other work that we are doing is that there are different network topologies that can be actually studied to see how well our framework works when we have different connection strategies among agents in the network. For example, we could have some local subnetworks that are communicating just with the bridge node to another local subnetwork, and but also the heterogeneity of the network topologies it needs to be investigated. And other than that, we use the simple classifier with the RVFL, but we can also see what happens if we use randomization with deeper reservoirs, and what happens in these cases. Thank you for your attention, and I'm here for the discussion and for any question that you might have.
Thank you very much, Antonello. Thank you. So now we have quite some time for questions, please. Feel free to unmute yourself and speak up. Maybe to warm up, I have a question on my own. My question concerns the accuracy figures that you showed on most of the graphs. So in real applications, like you told me before that you're working with prediction on energy data or prediction of this and that. So in real applications, so this, I mean, these kind of figures, accuracy figures, are they considered as acceptable, like 65, 75? So what is the target accuracy level?
Well, the question is interesting, and we have to be reminded that we are always comparing ourselves to the local agent, where we deploy a single sensor that has a single problem to solve, for example, of prediction and classification. So in some sense, while the accuracy can be thought of unsatisfactory from what we have seen, in reality, what we're seeing is that we need some method to just improve those accuracies. And of course, the actual absolute accuracy is something that depends on the single application. In some applications, 0.6, 0.7 can be some information that can be actually useful, and in some application we need some more accuracy. In fact, if you remember, they were very spread out in terms of accuracy. Some were around 0.6, some were around 0.9. So the absolute value depends on the actual application. But the relative value from the distributed with respect to the local version is what actually it's interesting in this kind of framework.
Thank you. Let's see. Ross switched on his cameras, meaning that he wants to talk.
Thank you for that. I'll just carry on from the conversation you've just been having with Evgeny. I was just thinking about the definition of the task that these distributed sensor systems are supposed to be undertaking. And obviously in the analysis you've been doing, your classifiers have been for as many classes as each of the UCI data sets have been using, so that the number of classes will vary across all your data sets. But if we just, for the moment, consider the case where there are only two classes, so binary classifier, one of the issues with accuracy as an outcome metric is it's not really well behaved when you start talking about the baseline rates for the classes in the environment varying. And when I was thinking about that, it occurred to me that if you have distributed IoT devices, then it may well be the case that the baseline rate may vary by IoT device across all the places they're distributed. So if it's something to do with a thermostat, is it too hot or not? That one which is in a bedroom may want to have a different definition of what's hot compared to one which is right next to the hot water heater or something like that. So that would seem to make the overall process of assessing the performance of a network like this more difficult, because I mean, if you were accepting that the devices are likely to have different baseline rates for all the classes between each of the IoT devices, then essentially you'd need to optimize the class bias, the threshold between the two classes on a per device basis. And if you didn't do that, then you're not really letting the system perform as well as it might. Have you got any thoughts about how you might deal with that, or whether that even makes sense as an idea for this sort of network?
It does definitely make sense. Thank you for the question, and it sparks a very interesting discussion, because we are thinking about here. What we did here is just we took a single data set and we split over the network, but so we are actually solving a problem that is in a cooperative way. So we have the same problem split among all the agents, and each agent that is own single problem to solve, but they pertain to the optimal global solution. And in the cases where these single local data sets are not actually part of, or at least are not weighted in the same as the same in the optimal classification, prediction problem, whatever problem might be, this is a problem. And what we did some work on that, but not related to HD computing. And these cases are solved with complex consensus algorithms in cases when we have different local problems, but similar local problems, but a different global problem. And in those cases, we tend to weight the consensus in a way that each agent of a single sub-network that are deployed in different areas of space are let me put it this way. There's always some information that can be shared to be able to improve the local version of the solving of the problem. But how much to wait and to take care of the information of the other agents that is coming to a single agent is demanded to the global definition of the problem. And this is of course dependent of the single application, and as I said, can be solved with complex consensus algorithms that are weighting those things out.
Yeah, yeah. So you're saying that the problems you're trying to solve with these are essentially global problems. Is it ever the case that it's actually local problems that you're trying to solve at each of the IoT devices, but that, as you said earlier on in that answer, that the situations that each of the IoT sensors is facing is similar, so that they can learn things from each
Exactly.
other,
Exactly.
but that but it's a local problem. I mean, although you've presented this in as a classification problem, for most techniques, there's usually a regression model hiding underneath the classification model. So you've got some small number of classifiers, classification methods, where it's inherently a quantized output. It's one class or another class, and there's no way to recover a score, a continuous score from underneath it. But for many classification processes, actually the first step is calculating some sort of a score, equivalent to what's the probability or likelihood that it's this category or that category. And then you have a decision process which sits on top of it, which turns those continuous scores into the quantized classes. So yeah, it could well be that what you're doing by combining the information across the IoT devices is trying to improve that underlying scoring system, and that but making the best decision out of that scoring system, it then comes down to some sort of another adaptation at the per IoT device level to deal with its own local environment. But if the underlying dimension that the classification is based on is the same across all devices, then you obviously it's helpful to get
Yes.
everybody else's mixed in.
Exactly. This makes total sense. And we in my PhD thesis, I worked on distributed clustering problems that are, of course, not classification problems, but in which they are thought of differently. But a kind of similar way, I developed a system where each agent computed some local representatives of the data, some local scoring mechanism that could also be shared in this network, and with a consensus algorithm, they could actually grasp some underlying, let's say, underlying rules of the model that were clustering, and then the local clustering will get better by just sharing this information among these nodes. So this, yes, it is definitely the case.
I wonder whether, in terms of the assessment, so all the results you showed were in terms of accuracy, but I wonder whether, because that is necessarily mixing in the decision process in with the discrimination process, whether it might be helpful to do your analysis in terms of the underlying continuous class scores. I have no idea whether that would be better or not, but it is just,
Yes.
it's excluding the decision process, which might perhaps be a source of noise in your comparisons.
Yes, it's definitely something that we can test. Thank you for the insight. And elaborating on this point is that each problem is different from the other. So in theory, also the average accuracy for a method makes sense, but can also be thought as mixing things up. So if I'm evaluating the average of accuracy over 100 datasets, it's meaningful in the sense that I'm getting, for the same datasets, I'm getting the mean values for two different methods, but between each dataset, the actual mean of accuracy, it's kind of the only way to see it, but it's also less meaningful in some sort of way of thinking.
Okay, thank you. Very interesting.
Thank you very much.
So let's see if there are any more questions. Well, if any, we always have our mailing list or write directly to Antonello.
Yes, for sure.
Maybe Antonello, it's a good time that you pre-announce that
Yes.
event that you were talking about before we started.
Yes, thank you for the opportunity, Evgeny. As you may know, the next year the IGCNN conference will be held in the framework of WCCI conference and will be in Italy, in Padua, not in Rome, but still closer than most of you will be. And today I submitted a proposal for a special session on hyperdimensional computing. And so I will be glad if it's accepted that you may submit to this special session. I will co-organize it with Massimo Panella, which was my PhD supervisor and with whom I'm collaborating. And I will send you a reminder on the group to give you all the important dates for the submission. So you can think about submitting some hyperdimensional computing works relating to specifically to neural networks.
Yes, thank you, Antonello. And I think this is a great opportunity for all of us. And if you need help with reviewing papers, you can also recruit us to your team.
Thank you very much.
So indicative to all the people, so the deadline normally comes end of January for GCNN, and it's considered to be very one of leading neural network conferences. Right, okay. Thank you very much for your talk, Antonello, once again. And thank you all for attending this talk. So we see each other in 2 weeks from now. So thank you very much.
Thank you very much. Bye-bye.
Yeah.
Thank you, Antonello. Thanks, Evgeny. Thanks, everybody. Bye.
Yeah. Bye.